Good evening, 2021ers. This is Professor Kaufman, and this will be an introduction to Project 3. At the end of this, you should be able to get started on the project and be aware of some of the issues that are at stake associated with the two problems that are present here. As was Project 2, this one is divided into two parts. The first problem will have you coding things, reworking the LCD clock functions that you previously wrote in C and rewriting them in assembly instead. This will be a good opportunity to practice coding assembly and gain a deeper understanding of it through writing that kind of code. Second problem will involve a debugging exercise similar to the puzzle box, but this time you'll be given only a binary executable. That will require you to make use of GDB in a form that's associated with disassembled code. You can always take a binary and convert it into some textual form of the assembly code, even if it was converted down from C. That assembly code has more or less one-to-one correspondence to the binary stuff that's actually in the executable, so you can look at the low-level instructions there. As usual, there is a code pack. It's up here, and we'll download it in just a second after taking a tour of what's here. And as well as that manifest that lists the files that are provided, those that you'll need to create, as well as a few other things. As for the first problem, there are a couple interesting things to note. Since this is a rehash of what we did in Project 2, it's wise to have on hand a copy of your clockupdate.c. This is the source file that you will have completed as part of Project 2. In the event that you didn't complete that project, don't have working code for it, or you feel unconfident about your solution, perhaps you couldn't figure out a way to do this without some deeply nested conditionals or something like that, it would be wise to approach a staff member to get some insight into this. There's a specific provision for this mentioned down here in the section that talks about hand coding your assembly. It's here that if you weren't able to complete Project 2, you can meet with a staff member during office hours, either in person or online office hours, and tell them I'm here because I don't feel good about my solution or I didn't finish it. They'll be happy to then talk over the parts that were difficult for you and walk you through a version that comes from me, the solution to this that I provided to them. And at the end of that discussion, they will provide it to you so that you have a roadmap that's reasonably straightforward as you go to convert some C code into assembly. A straightforward roadmap like that makes the job much easier than if you have a meandering path there. Don't hesitate to make use of this, but if you are pretty satisfied with your solution to the Project 2 C code, clockupdate.c, just bring in that solution here. It's not so much that anyone's going to check that you exactly follow your solution in C in your assembly version. It's just that having a roadmap of what to do when there and some C lines that you translate to assembly makes it much easier to handle. Along with that, then there are a few other caveats here. All of you should realize at this point that you can use the compiler to generate from C code assembly code. Generally, though, this kind of generated assembly from compilers is easy to recognize. It'll have a number of features like numeric label names like .L1, .L2, .L3. It'll use a certain pattern of instructions that are selected that are not as easy for humans to read, and it'll be utterly devoid of any commentary. So to that end, no credit will be given for completely compiler-generated code. In some cases, it may be worth your while to generate some assembly from the C code that you had, but most students find that reading that stuff is very difficult, and better luck just starting from scratch, converting your C code to assembly in a more or less line-by-line fashion. Make sure then as you do this to annotate your assembly thoroughly. One of the most common pieces of feedback from students is that what they really needed to do was to comment virtually every line of their assembly code, along with block comments to indicate things like, for this portion of the code, I've decided for this C variable, my number of seconds since the beginning of the day, I'm going to put that in this register. It's easy to lose track of those kinds of details, and you're doing yourself a favor then to document your plan so that it's easier to verify assumptions when things go wrong, as they will go wrong. Use informative label names as well, so you need to jump to locations, describe what you're doing at that location in the label name. Your readers will appreciate it, and one of the readers in this case will be you. There's a number of other general comments on being safe as you code assembly. And one of the great favors you can do yourself is to set up your editor so you at least get syntax highlighting associated with this. There's a short YouTube video I'll link here for that. But I'll say more then as we actually get into this. And you'll refer often back to this diagram of the basic general purpose registers that are available in x86-64. It's handy to keep this around at all times. For now, let's actually set this thing up and get to it. There's only one required file to create, this clock update asm.s. But we're going to download the code first, and then we'll create that template based on an outline that's actually provided in the project spec. I'm going to first copy the link here that's associated with this thing, because I'm going to log into one of the lab machines and make use of it. So I'll copy that link address. And over here, I'm going to SSH and a terminal into login01.cslabs.umn.edu. This may take just a moment, and then we're in. I'm an Emacs man myself, so I'm going to fire that up right away because we can make use of it for terminal and so forth. And here, I guess, yeah, I don't really have anything in here that's like super necessary. So let me fire up a shell first. And then I'll use the wget command to download the code into my home directory here. Should take just a moment. Slower than I thought. I guess CAC Labs machines are working hard this evening. All right, so with that downloaded, I'll issue an unzip command here for p3code.zip. I should fire this up. And because I just want to have a quick visual look in there, this p3code.zip, you can see the files that are in here. The first one that's listed here, bombdownload.sh, we'll get to momentarily when we get on to the second problem. But the remaining files in here will be familiar. They all are copies of what was present for Project 2. As basically, we're doing the same thing, but in assembly this time. So the main function, the simulator function, the header file, the testing stuff, it's all identical because the code that's to be added to it is in assembly. Let's do so now. I am going to create a new file, and it needs to be called clockupdateasm.s. The .s, again, is an extension that's associated with assembly, and this is where I'm going to end up writing stuff associated with that. Initially, I'm just going to find in here there is a structure of clock update asm, and this is more or less an outline of the code that's going to be required, along with some commentary and a few tips and tricks in here that'll prove useful. It's not going to compile out of the gate, but we'll get it compiling in short order here. But I'm just going to take this section here and copy down to the last bit here. Buzz over to the terminal and paste that in. You can see Emacs for me is already set up to do syntax highlighting, so certain of the assembler directives, like these text and global directives, they're highlighted with names, not so, but comments are clearly delayed with the bright orange color. Now, as I would save this thing initially, there are a number of things wrong with it. And if I buzz back over to my shell and do, let's see, let's change into P3 code here and do a make, you'll see that there is a syntax error in the assembly file that the assembler isn't having. This is code that's there to sort of apprise to some techniques, but is not compilable. So let me change back over here. It's this right here, which one of the first steps we're going to need is to access a global variable in our first function that's set TOD from ports. But for now, I'm just going to comment this out because I don't want to use it yet. Not sure. There might be a few other things in here that are, oh, that's actually it. One other thing, though, that is important to realize, let's see, this thing has function names in it, but no returns. So it's going to behave rather strangely if I don't do something else here. So to mitigate that, let me just pop down a ret instruction at the end of each of the three functions. So up here is the label associated with the first function. You can see it's identified as a global symbol, and we'll talk about that later, and it's in a text section. That means that everything that follows this directive is executable code. In an assembly file, you can change this then to a data section, which allows you to establish global variables. So here, the labels would correspond to data, and we'll use that later in the second function. Importantly then, as I move down, I want to change back to a text section as I'd want to write another function over here. And so I'm going to plop down a ret instruction here. This stuff is going to be trouble later on because there's no global variable. Actually, there are global variables that are associated with that. So I'm going to comment it out anyway just because I'm not sure I want that to happen. And then finally, the third function, clock update, is down here. Let me add as well a return instruction here. Now, with those things in place, these comprise, limited but functional routines that the C testing framework can call. To demonstrate, if I jump back over here and do a make again, I should be able to do a make test. And this will certainly fail all of the tests here because there's no functionality in the different functions. So as I'd call test clock updating this set function, the set TOD from ports, it's not going to do anything. But I could at least look at the results file over here and you see, all my stuff is wrong. As I do that thing, I return a random value. So clearly nothing's going right here except that I can run the tests here. So one thing I might do out of the gate there then is to buzz back over to the assembly file and at least do something like return a value over here. In that case, you'd need to know which register needs to be the return value for these functions. If you forget, then it's wise to sort of check back over here, find that little register summary diagram, and consult some of the notes. When we get to calling functions, some of those are going to go into arguments registers here, for instance, the first argument in RDI, but we're interested in this case in the return value. And as this function is supposed to return an integer of some type, we'll favor EAX for that. As you'd forget, you may want to refresh your memory of how this stuff looks by looking in clock H, and here you'll see the prototypes in C for those three things. This set TOD from ports takes one argument and returns an integer. This takes a couple arguments and returns an integer, and clocked update takes nothing and returns an integer. So let's just buzz back over here to this. We need to put something in EAX. It looks like from the commentary that was given in the test file, that was over here, the test results indicated on the left-hand side here, it should return 0, but I'm returning whatever happened to be in EAX before that. So let's at least push R0 in there with a moval of 0 into EAX. And if I just rerun that first test, so make test num equals 1, then I'll see this on the screen here. Some problems here with conditional jumps and so forth. But at least up here, it asked me to return 0, and I've returned 0, so that's all good and fine. I haven't done anything with this TOD here. And importantly, you'd want to figure out where is this time of day struct coming in. If you look back at the clock header here, you'll see it's coming in as the sole argument to this function as a pointer, TOD pointer here. And if you're curious, like, well, how does it come into an assembly function like that, then consult this table again, where you'll find the first argument to functions, by and large, comes in the DI family registers. If it's a pointer, it'll be the full 64-bit with a pointer to contain an address for that, RDI here. And so I might make a note of that here in my assembly file here, that RDI is a pointer to the to a TODT struct. So that means that you can do things like if I moved just some value like 5 to where RDI is at. This is going to change whatever is at a 0 offset from the beginning of the struct. And at this level, like a 0 offset like this. Whereas I could also plop down a 4 offset here, which would move a 5 to some part of that struct. Now, it's a good idea then to know, well, where are the parts of that struct stored? And there's commentary on each of the functions here that is designed to help you understand that. A little reminder here of what the function is supposed to be doing and so forth. This table here summarizes as you deal with a pointer to a struct, one of these TOD structs, there are various things over here that would allow you to plop down values as fields of those structs as it's in main memory there. For instance, we're more or less copying this movl $5 to 0 off of some register, happens to be an RDI. We can verify that if we bop over the shell, rerun that first test, which should recompile and then rerun. If I come back up here to the results, you can see here the daysex, which is the first field, so it's at 0 offset from the beginning of the field. It's got a 5 in it now, which is still wrong, and I'd need to do some computation eventually to figure that part out. But at least this gives me the ability to modify and change that struct in a sane fashion. As you want to change others of the fields, then consult this table over here for that. Finally then, there's one tactic then that's mentioned in the commentary down here that I need to access a global variable in this case. And if we look back in the spec over at the description for this, I'm supposed to read the time of day port global variable and then convert that into a number of seconds since the beginning of day, possibly doing some rounding and so forth. So to that end, it's you'd want to know, how do I access a global variable in assembly? The syntax for that is alluded to here with the move instruction used, and you'd want to pick a suffix here that's appropriate to the size. In this case, that time of day port has a 32-bit integer in it. Number of seconds relates to the number of seconds since the beginning of the day. So I'd want to use a move L here. This some global variable named here then is the name for the global variable moved. We'll take an offset from the RIP here, and this is a weird technique that we'll briefly talk about in our coverage of assembly, but really won't make sense until later in the class when we get to our unit on linking, because it involves linking several .o files together to create an executable, at which point the location of global variables is actually known. They're all glommed together into a single place. And it's only then that this some global variable thing will be filled in with an actual number that tells you some offset from where the RIP is at. That's where this particular global variable is at. And then, of course, we have a destination register. So I'll be just slightly lazy, and I'll grab this movl over here and copy that in up top to get me started. Oops, I need to use a different paste here. And so, for instance, let's see, I'll tab that over. I could take that value that's in ECX and move it directly into where the 0th field is, and we should see it there. So then if I change back over to the shell and make this and run it one more time, you see, oh wait, shoot, I think I got the, oh, it's yeah, the 0, the port value is 0 over here. So the time of day port here is set to be 0. And so I'm moving that 0 over here into this thing, which isn't exactly what I should be doing, but that'll be fine. Let me run this second test, which will have a different value for that port, so we should actually see some differences there. Let's see, or maybe not, it's still set to be 0 in the second test, so let's try the third test here, and just, I'm looking for a change there. Yeah, so here you can see up top the time of day port is set to something up here, and that is whatever that value is. That's 360 plus 45 all by 16. That amounts to 3600 apparently, and this day sex is set to that because we read that global variable and we plop it down over here. And that's going to need some conversion because we'll have to divide it by 16 and then take a remainder and do some rounding to get the actual number of seconds, which is apparently 225, but that's part of the fun that all of you engage in. some hints about implementing these things are given later on down here. Take care, absorb that, try some things. You'll certainly end up having to do some error checking as well to make sure if this thing's negative or too big or something like that. You attend to that. But this part isn't too bad. You'll have to exercise the division instruction as well to compute the minutes and hours and so forth here. But generally, this isn't too bad if you get an early start on it. Similarly then, the second function has documentation associated with it. There's some advice then as you're dealing here with not a pointer to a struct, but a packed struct. And since the struct is large enough, it actually gets packed into two separate registers, the first two RDI and RSI. And the table that's given here then says within those registers, all the fields of the packed struct are present. Some of them are in the first RDI register, some are in the second, but you'll use techniques similar here to what you'll have done in Lab 7 to extract those fields from the registers through shifting and anding. And some of the shift hints that are given over here are useful for that, as largely the second function here needs to deal with the minutes, the hours, and maybe the AM, PM to construct this display, which again will be created using shifts and ands and so forth. As you did in the second project, it's useful to have an array of different values that are the bit strings that represent, this is how you would draw on that LCD display, a 7 or a 2 or a 9. Here is in the middle here, this data section, a way you can set up arrays of values. A single global variable like myint can be set up over here, but things that you plop down here associated with the label as you do them in sequence, this is more or less multiple values in a row. This is an array of 3 values that are over here, each of integer 4 byte size. And as you'd want to load up the address of that array, there's some syntax given in here to say, oh, I want to move one individual value into a register, or I want to use a leak to load the address of the beginning of the array into the RDX register. So make use of those in a fashion that is similar to what you did in C, where you do some division to say, I figured out that the ones digits of the minutes is a 2. Let me go to the 2th index of this array to fish out a bit string and then OR that on to some master register there. All right, that's probably enough of me blathering about this part. Good luck to you on that. The second problem then is similar to the debugging exercise that we did in Project 2 and is a classic assignment that was put together by your textbook authors, known as the binary bomb. This is a bit involved because it first involves you downloading an executable that's tailored to you somewhat specifically. As you download these, they're constructed from some C code, compiled, and what you get is an executable, although there'll be an intermingling of different phases and variants of them, so no two students will necessarily have the exact same set of phases that they're working on. Generally, the phases increase in difficulty, so the first phase is relatively easy, and we'll actually solve it together today, although my specific solution may be a little different than yours. Versus then the second phase is a little bit more tricky, third phase gets harder, etc. You'll have to figure out inputs for this using a combination of debugging and some other tricks there. So it's very useful to know how to use GDB, and we'll set that up as well here. So over here, the first thing you do is to get a bomb, and there's this provided script here, bombdownload.shell. If you're so inclined, you can also visit the following websites, Bomb Labs, CSE Labs, and so forth. However, if I just clicked on this right now, and I'll open another tab, you'll see it just hangs. And that's because it's behind the CSE Labs firewall. So I'm off campus right now, I'm accessing it from general Wi-Fi, and this is not going to work. If you clicked on this link when you're actually on a lab machine, or on one of the remote login machines, which you can try in just a minute, that you'd get to by visiting a certain site here, which gives you a graphical Linux interface, and then you can open a browser within that. Then you'd actually connect and be able to download a bomb here, see the scoreboard, etc. We'll do that a little bit later just to make sure that we made some progress on this thing. For now, though, I want to move. I'll just use the bomb download script here. So bombdownload.shell. It should fetch a bomb for me. It'll default to your username over here, which is just modestly important. And this will go into a little subdirectory bomb 00009. Apparently this is the 9th bomb that's been downloaded. And we'll unzip it in just a second. You're free to download more than one bomb if you want, but importantly, the scoring works as whatever the farthest along phase you've gotten in any bomb, that's how much credit you get earned. But as you might lose credit by inadvertently putting wrong inputs in and then running the bomb to completion to explode it, this will lead to a loss of credits. And if you have several different bombs, all of explosions, then they add up for all of them. There's a modest amount of credit that you lose for this. It's all extra credit, or makeup credit rather. So it's not like you can't get 100% on the assignment without it. You just lose out on that part. And if you're particularly interested in the scoring, that's listed down a little bit lower. Then I may as well mention it now. This has a total of 6 phases. And you only need to complete the first 5 to get full credits. So the 40 over here is 40% of this project. If you manage to finish phase 6 or avoid all explosions, then there's 5 bonus credits associated with this. If you do both those things, then that's 10 bonus credits, or makeup credit as it were. And if you're really curious, there's a complex table about if you got this many explosions, etc. But if you're diligent, you won't get any explosions, and we'll show how in just a second. Once we actually start passing some phases, we'll have a look at the scoreboard to make sure that they're being registered. So as you did for Puzzlebox then, I want to unzip this thing, 009.zip, and maybe we'll change into that subdirectory now. And have a look around. You'll see there are 3 files. There's README, which says who this belongs to. There is a bomb.c file, which has a small amount of source code in it. There's a little bit of setup here, but then this more or less boils down to a phase 1 function, a phase 2 function, a phase 3 function, etc., through phase 6, that is down here. And that's it in terms of the C source code that you're given. The other part of this then is the executable itself. And we'll do something just slightly dumb here. We'll run the bomb. And this will just wait for a prompt in which I can type some stuff here. Should I press enter right now, this is going to accept that input, which is in all likelihood going to be completely wrong, explode the bomb, notify the server of that fact, and lose me a little bit of credit. So I'm going to bail at this point by typing Control-C with a mild little joke here, but no harm done in that respect. This is not the way that we want to go about this. First and foremost, this thing is meant to take as an input file so that you don't have to type the inputs that are associated with each phase. And so we'll eventually want to run this with bomb and then inputs.txt. I should create that file quick, so let me put it in here, input.txt. And here, I don't need to put my x500 or anything. I'll just put like test input down over here. Save that, and then we would rerun the bomb here, .bomb with inputs.txt. But importantly, I don't want to press enter now, because if the bomb were to run, it would read the input from this file, find it to be wrong, and explode, which would lose me credit again. So I'm going to put the ixnay on that. Instead, what I really need to do is to run this in the debugger, so I have complete control over the stepping fashion that happens here. Emacs is a little bit wonky for running the debugger, so I'm going to exit that for just a moment here. Change into that, let's see, P3 code, and then it'll be bomb9 here. And here's where I will want to fire up the debugger for this. I'll run it on GDB bomb. Yeah, I think that'll do it. Maybe enable the TUI node, which you could also do on the command line if you want. And I'm going to break at main to begin with and do a set args of input.txt. I've got a breakpoint set and we're good there. And so then I'm going to give this thing a run. So here I'm in him in main. And what you'd find is I can do a bunch of steps here to sort of step forwards through some stuff. I actually want to next over this stuff because I want it there. Next over this because there's no point in looking at that thing. Next here. This input will read it. And then we're at this phase 1 part. Now I don't have access to any of these read line or anything, but most of the action is going to be in this phase 1 function, phase 2 function, etc. And so here is where things get a little bit interesting. I can do a step, which would normally go into a function. Oh no, I persploded myself. Crap. Okay, well, that's okay. The first one is free, and I can guarantee they will never let this happen again. The way to avoid this is to set a breakpoint at a particular routine. And the routine that you'll all want to be aware of is explode bomb. You can actually get auto completion, so I start to explode and then I can press tab here. This will set a breakpoint so that if I ever were to inadvertently step too far again like this, then I'll end up hitting the breakpoint that's at this routine, which is part of the compile code, and won't actually explode the bomb because I'll have a chance to say, oh, I'm at the explosion, I'm going to back up and try something else here. So let's run that again. And this time I'm just going to continue. And because I'm confident here, yeah, whatever was happening there, I hit the explode bomb, but it's okay. It hasn't exploded. It's just starting, and I can back up now and try something else in the debugger. Well, first thing might be, let's set a breakpoint at this phase 1, is it? Yeah, like this. Okay, and that's good. So I'll give it one more run. And I'll continue at this point. And here I'm at a breakpoint for phase 1. But very unfortunately, I have no source code for it. It's not in C anymore. It's in the binary executable. Now is when the fun begins. Change my layout to actually look at the assembly code. Since it's a compiled binary, there are bytes in there representing the binary form of those instructions that the debugger knows how to reverse to put back into their textual form to show in the debugging session. And so here's a series of assembly instructions. That's good to know about. At this stage, then, I can start stepping by not whole C lines, but stepping instructions. Step I, or SI for short. And this will carry through the different functions that are present here. I can even step into this strings not equal routine over here. If I didn't want to step into it, then I could do a next instruction, which would pass over it. As I could continue to step here, I just hit a line here that is suspiciously bad. It's about to call the explode bomb and that thing. So apparently something's gone wrong, and we'll want to have a look at how that goes and figure out things more. But here's where then I don't want to land on this line. I want to do something else that would get control flow through this thing. So let me do a rerun at this case stage. Let's see. So here I'm at the beginning of main. I don't really want to break at the beginning of main anymore, so I'll only delete that breakpoint 1 so I don't do there. And I'll continue now to what the next breakpoint is. Press Control L to refresh the screen because some output got there and things got garbled, and now I'm back at the beginning of phase 1. All right, now I have to be on the alert because I actually need to start understanding some of what's happening here in this assembly code. It's good to be knowledgeable about this function. Phase 1 has passed some arguments in some spots. And just as we did as we writing our own assembly, it's good to review where the arguments come into functions here. Let's see, let me find that register summary diagram. The first one's an RDI. So let's just have a quick look here. I'm going to pull up using layout regs, the register file, so you can see it. And here's RDI. It's a big honking number. Well, this here looks suspiciously like a memory address. And if I recall right from our main, it's actually passed an argument that's some sort of a pointer called input. So let's inspect this thing. It's a memory address. I could print it out, say print out RDI, but that's just going to show me this number up here. Or if I printed it in hexadecimal fashion, then I'll see the same thing that it's up here. What I really want to do is examine what's at this memory address. So instead of print, I'll try an X. So here's X, maybe it's a decimal number. Examine what's at RDI. Let's see, 193, that doesn't make a lot of sense to me, but this part, input strings, as a labeled part of what is in the binary, that's, hinting at something that maybe this is actually character data instead. So here I'll change the flag on X to examine this as a string instead, and oh, well, that's familiar. This is the input string I gave from my input.txt file. Cool, okay, so the first argument is the input string that I gave it. If I'm looking ahead just a little bit in the source code, I'll see a strings not equal over here. This is preceded by an LEA instruction. For those who don't remember, this is load effective address, as in calculate the address of something and plop it down in a register. Looks like it's going into RSI here. Now why RSI? Well, if you take a brief gander over here at the register table again, RSI is the second argument register. Since between the beginning of this function and this call, there's no changes to RDI, it's set up to be the first argument to any functions I call, and this sets up a second argument. Now this part, the strings not equal, makes me think it's probably comparing them. And since as soon as I get back from this, I do some sort of a test involving EAX, which would be the return value for this function, it seems a fair assertion that maybe this stuff is comparing the string I give it to some other string, and then checking something about the equality of those two. So let's step a few instructions forwards. I'm about to call this function, and I actually want to know, what are you comparing my string to? It's in RDI, but RSI just got loaded up with something. You can see also looks like suspiciously a memory address. So maybe I'll do an examine as a string here what RSI is. And it is the string y makes trillions when one could make billions. So that then as a sort of hint might make us sort of think, let's try this thing as a string instead. So here I'm going to use a couple tricks that are worthwhile to know, as if you're in a terminal session only, this can be a little daunting. But I'm going to copy this. And in your kernel session, if you hold Control-Shift and then C, this usually causes your terminal emulator to copy something in a normal sort of cut-paste copy fashion. And the second trick, extremely useful for programs in general in the terminal. If you press Control-Z, this will suspend a program, including GDB. And down here, I have a couple programs running now. I've gotten back to my terminal. I can type jobs and say, oh, that Emacs session, I didn't actually quit it, I just suspended it, it stopped it. And I've also got a second job here, GDB. I can recall this thing. So, for instance, if I typed foreground right now, GDB is the most recent job that I had going, so this will get me back into the debugger. Another press of Control-Z will get me back to the terminal. This suspends it. If I wanted to recall an earlier job, this #1 Emacs job, let me foreground that and use a %1. This is a shorthand for job #1. Put that in the foreground, and voila, I'll get my Emacs back. Okay, so here I had just created this input.txt. I was trying test inputs, but let's paste in this other string instead. Okay, with that there, I've saved the file, and I know the GDB session is positioned more or less right to be safe and do analysis. So let me check again. It's job #2, so I'll foreground GDB here. And since I've changed the input, I need to rerun from the beginning of the program. So I'll type run again here. My breakpoint stops me here at the beginning of phase 1. If I examine what's in RDI, this should change, and it did, to the new string that I had in my input.txt. I'm going to step a few instructions here, and then check, is this RSI, that's still, yeah, why make trillions to billions, so they match. Now, I could go into this strings not equal instruction, but I'm not terribly interested in looking at that code yet because I have a strong suspicion that might work. So I'm going to try a next instruction, which will pass over the call to that. I'm getting back here. The EAX register, it's changed and it's a 0. If we follow the normal conventions of this function saying strings not equal, if it's returning a falsy value to indicate they are equal, and a truthy value to say they're not equal, as the name would imply, this 0 is a falsy value, so that would indicate in the converse they are equal. So we can check that here, that there's a jump here for in the next instruction for not equal. And that jumps down here to the phase 1 plus 29th byte, the call queue here for explode bomb. That's where I don't want to go. So I'm really hoping then that this jump is not going to go there. And it's a jump not equal, which would be triggered by, a non-zero value here. So I think we're actually going to be in business. Not there. And instead I'll fall through to this return instruction, which is going to pop me out of the phase and plop me back in main. So I'll do this in here, and I'm back up in main. If you care to, you can actually change this back into the normal C source mode, layout source, because we're back in C mode here. Not necessary, but you'll see now we're about to run a function called phase diffused, which is going to net me some credits. So let me just do a next here for this part. Let's see, not sure what's happened there. Let me try a layout asm to see if I just did a bunch of stuff. There's, I guess, a little confused about this part, so I guess we'll have to be a little more careful on that. I think at this point what I want to do is I expect from the C source code that there's also a phase 2. So let me just break at phase 2 there. And I'm going to use the continue command, which says keep running until you hit a breakpoint. I feel okay about this because there are a couple breakpoints now. If I type info break, it'll show me there's one at phase 1, there's one at phase 2, but there's also one at explode bomb. So if I've done something wrong and I'll hit an explosion this time, I'll hit the breakpoint first so it won't actually explode. So I'll continue. I get some output here. How about the next one? So I'm just going to try and type some inputs like hello. I'm betting right now it's trying to read from the input file, but there's nothing left in the input file. And yeah, okay, so I landed in phase 2 this time. So, and I'm betting then that, let's see if I bring up the registers again. Here's RDI, it's another memory address, and if I examined what's at RDI, it's the string hello. Okay, so that's what I just typed. So it would be at this point time to start adding in some more strings to that input.txt file so that I can continue sort of into this new phase and try and figure out what's going on with this one. Does it take one input, two inputs, etc.? And so you'd want to sort of look around for hints about how many inputs, what type of inputs they need to be. But I think that's where we'll leave off at this point. All right, a couple other tricks to know then. We've seen breakpoints and GDB is extremely useful. But as we discussed in lecture, it's also useful to have a more complete view of what's in the BOM than what you can see in the limited window that GDB provides. So there's a utility that we talked about, object dump, and it has a disassemble option. So that if I were to do this on the BOM, it's not going to run or anything. It's going to say, go look at those bytes and convert them back into textual assembly instructions. So as I punch that, you'll see a stream of text fly by here, which is everything that's in the BOM right now. And if I dump that into a, let's see, bombcode.txt here, this indirection here, or redirection rather, would take what would go on the screen and put it in this bombcode.txt file. Then I can foreground my Emacs over here and say, here's this bombcode.txt. And at your leisure, you can start scrolling through all of the instructions that are in the BOM. might look for instance, phase 1 here, and here is phase 1 in all its glory. I can even make notes about things like phase 2. This is, doing something about moving. Oops, I don't want to do the line breaking here. Moving something into the stack, if that's what I think is happening here, and so on and so forth. To that end, being able to disassemble this thing and actually look at it in its entirety, take some notes about it, try and figure out control flow and relations between things, extremely useful. That, I think, should about do it. The last part I wanted to look at then is to see if the progress I made was recorded on the scoreboard. So the link for the scoreboard is given over here, but again, I can't log in directly for this. Instead, I'm going to go to one of the lab machines. So this would be CSC Labs, Keller Hall 1250. I have a session running already there, I think. So if I can recall this thing, and let's see. Oh, wow. Zoom decided it wanted to start over there. You can go away. So then I could grab that link, which I had here on this part, and paste it in over here. You can see I've already got it pasted in there. Let's just make sure that still works. And bomb number 9, I've got 1 phase diffused, 1 explosion, but 15 points total on that. So doing well, and have some neighbor over here that's made a little bit of progress as well. Wow, is the first phase really worth 15 points? Is that how I scored it? Well, oh yeah, that's right, because I still have my bonus code here for not having exploded much yet. So that's the 15 points total just for getting the first one in and not having any explosions yet. So cool. Okay. So that's good progress, and all of you should be able to bang out that first phase in no time flat. Second phase gets harder because you're actually going to have to look at several things and do a little puzzle solving, but hopefully Puzzle Box prepared you for that. That's all I've got for now. Good luck to all of you. Have a wonderful spring break if you're watching this beforehand, and I hope you had a wonderful spring break if you're watching it afterwards. During the first week after spring break, we'll have some tutorial sessions that aid you for both of those problems. Look forward to announcements for those. Take care, and happy hacking.